magnetic field. We're going to study how different currents can create magnetic fields. 3 different topics: long straight wire, current loop, and solenoid. The magnetic field created around a long straight wire covers the entire space around it. So if a wire is much longer than the distance of a point in space to this wire, so the L is much larger than the R. R is in the red color, represented by the length of that red colored arrow. So that is a long straight wire. So is 10 centimeter a long straight wire? Yes. If the 10 centimeter is much larger than the distance R. 1 meter can be long, 100 meter can be long if the length is larger than the distance to the wire. The magnetic field created is a vector, and the magnitude is mu0 times I over 2 pi r. Mu0 here is what we call the vacuum permeability constant. It's 4 pi times 10 to negative 7th Tesla meter over ampere. This is a universal constant, and it is also one of the 2 constants that define the speed of light. So this is the magnitude and direction of magnetic field around a long straight wire. So here it really represents the entire space, particularly the space that's close enough to this wire compared to the length of the wire. This is the first type. If we apply this first type and also combine with what we learned about the force on a current carrying wire, we can see that the magnetic field, if we have 2, this is an example, if we have 2 currents in these 2 straight wires that are going in parallel along the same direction, I1 and I2, then if we consider I1 to be the source of the magnetic field, that meaning I1 is the cause and the magnetic field is the result, is the effect, then the magnetic field is mu0 I1 over 2 pi r. R is the distance between the 2 wires. Okay, so what about the force on the second wire that carries I2? Well, the force is proportional to the length of the wire, so F is I2 times delta L times B. Here we don't have the sine 90 degree because that's 90 sine 90 degree is 1. If we combine the 2 equations above, we have that the force on the unit length equals to mu0 I1 times I2 divided by 2 pi r. So this is the force between 2 wires. So whenever we have 2 wires that's going in parallel, they either repel each other or attract each other. In the high voltage transmission lines, where we usually have a few lines going in parallel, if you can see, every some distance there will be a pole, and also on the pole there are a number of ceramic cups. The cups serve as the purpose of spacers that keeps the wires separated. So in case they repel or attract each other, the wires, we don't want the wires to touch each other. Okay, so this is an example. Another example, direction of force on electron number 1. So here we have electron number 1 and number 2, and the arrow next to it represents the direction of its velocity. Okay, we have a current I. So if we apply right-hand rule, if the right-hand thumb points the direction of I, then the fingers wrap around and represent the direction of the magnetic field. And at the point coming out of this paper or screen, coming out, at that point, the magnetic field comes out. So the dot here represents an arrow with the head coming out of the page. So if we use the right-hand rule to determine the force on the moving charge, then the index finger points the direction of the velocity, which is down in the page or on the screen. And then the middle finger represents the direction of the magnetic field, which is coming out of the page, perpendicular coming out of the page or the screen. And then the index finger will point towards the left. So this is the magnetic force on the moving positive charge. In the case of electron, it's a moving negative charge, so we're going to flip. The force is going to point to the right on electron 1 that's moving. That's the second example. Okay, so we covered the magnetic field caused by a long straight wire. Next example we're going to look at is a current loop. So we see the right-hand rule. If the right hand wraps around this, the thumb points the direction of the magnetic field, and the hand represents the direction of current. Generally, if the point is a distant z along the vertical axis in the page, that's the equation B is a function of z, the magnetic field. In the special case when z is 0, so if we want to know exactly what's the magnetic field at the center point of the loop, then B of 0 here represents the center of the current loop, equals to mu0 times I divided by 2r. R is the radius of the current loop. If we apply the right-hand rule, we can get the direction which is pointing upward. So this is the magnetic field of a coil. And remember, we only know this one point only, which is the center of that loop. At the center of the loop, this is the B. Then you say, what about the other areas of points? They are not so obviously having a simple math expression, so that's why we're not putting there, but definitely we can determine those. Those are just more complicated. We're using the simplest case. So here is an example. If we do have a current loop, and what is the current loop? Just try to crunch in some numbers to see how the magnitudes play out. So if we have a current that's 2 amperes and radius is 5 times 10 to the negative 2 meters, we convert those to SI base units. And what is the magnetic field? So just go to the toolbox, and this is we just learned at the center point of the loop, B0 is this value. So if we plug in the numbers, we have 1.2 times 10 to the negative 5th Tesla. So here is magnetic field. This is magnetic field inside a solenoid. So solenoid is a current loop with many turns. In that case, the magnetic field inside the solenoid, right? At any point inside the solenoid, meaning could be in the center, could be close to the wires. At every point is uniform magnetic field. Uniform magnetic field is useful because the examples we'll be using are all uniform magnetic fields. So the magnitude is mu0 I times n is the number of loops, L is the length, the physical length of the solenoid. So if we use right-hand rule, if our fingers represent the direction where the current goes, then the thumb points the direction of magnetic field. So if my finger points, hold around this, and magnetic field is going to the left inside the solenoid. So here, what's the magnetic field as an example? So if we know the length, we know it's 500 loops, and if we know it's 1 amperes flowing through it, what can we do to decide the magnetic field? So if we go to find out what's given, what's unknown, and also we have our constant. Look, you may not necessarily remember the value of this vacuum permeability constant. However, we do need to know it is a universal constant. All right, so that's if we know the solenoid's magnetic field, and then we plug in the numbers, we have 6.2 times 10 to the negative 3rd Tesla. So in summary, we introduced magnetic field that's caused by 3 types of current: straight current in a long wire, loop current when there's only one loop, a solenoid that's many loops. So we have learned how different currents can create magnetic field.